Hi, I'm Alejandro Hoyos, and I'm very excited to be here at the Intel Technology Tour in Phoenix, Arizona, in which we are unveiling our latest mobile processor architecture, codenamed Panther Lake. We get to sit down and talk to different Intel fellows and architects about the latest features that this mobile processor brings to the table. So join us in this video. So tell us, Panther Lake. What is Panther Lake? Can you tell us, succinctly, shortly, what is Panther Lake?
I would say Panther Lake for us was the next processor in which we have decided to take Lunar Lake into the mass production, meaning take it to higher volumes with additional performance, more segments, bring the Lunar Lake architecture into Intel process. So this is, in short, what Panther Lake is. To do that, we had to do several things into the architecture in order to fit things and make it work. But generally, it's taking Lunar Lake architecture, improve it a bit, and have it in higher volumes.
Oh, that's great. So from the architecture perspective, there's a lot of architecture scalability, right? Mm-hmm. And that comes through on kind of the different options, for lack of a better word, that we have, what different SoCs that we have there. Can you tell a little bit more like the different SoCs that we have and how this has helped us with the scalability?
Yeah. First, with all the constraints that we have recently, process, packaging, cost, even development cycles and so, we had to fit things to make things work.
Right.
And therefore, you need architecture that is actually flexible.
Right.
If you want to change things, if you want to do disaggregation or integration of components, if you want to change things, if you want to integrate new IPs, you have to do that very fast, and it has to be very easy in order to cope with all those constraints. So, and indeed, in Lunar Lake, we already thought about it, and some of the things that we have done helps us scale further in Panther Lake and also in later generations. So the first thing was actually building some fabric that can almost do everything. I mean, it can fit, can integrate every IP. It can communicate between tiles, different physical layers, and so very flexible. And we are building on that in order to build the next generations. And based on the needs that we have, whether market, whether cost, whether additional segments, we are building the chips in a way that it has, I think, before that chips was, let's say, one die, maybe two dies connected with some organic fabric.
Right.
Today is somewhat a system on a package in which you have many dies that you need to connect. It's more complex. You need to connect them with different IOs. So you need to have things that are flexible, that can connect things.
Were there any learnings throughout the previous processors that were applied this in order to help with the fabric or with the other IPs?
Yeah, definitely. So first we learned that we cannot control the different accelerators that we have with regards to the protocol in which they need to be connected to the fabric. So we had to design something that can connect to multiple type of protocols.
Right.
This was one thing that we learned. And we need to develop that inside the SoC so the connection will be very easy. The second was that instead of building some kind of a manual fabric that connects things, we had to build something that is more of a network on a chip.
Yeah, that makes sense.
Something that is automated and you can connect different type of IPs, each with its bandwidth and latency constraints and so it has to be automated. And the third was that we will probably need to cope with many protocols, meaning you need to transfer protocols across one fabric. You cannot build fabric per protocol. And therefore, we took all of those requirements and built one fabric that gives all of that. When you have such a fabric, now it's somewhat pretty easy. The fabric knows to connect different type of IPs, different type of protocols. It has one transactional layers. It carries over multiple functional protocols. It's much more, I would say, easy to integrate IPs like that.
That is pretty impressive because just you have multiple protocols in one bus.
Yes.
And because you have different IPs fighting or trying to get access to it. So it's pretty interesting to see how that handshake goes along there.
Correct. And we have bridges to bridge between the protocol that is internal to the IP and to the protocol that is running actually on the fabric.
One of the things that you covered in your presentation that caught my attention was pretty neat is the memory and the memory controller. So can you tell us a bit more like what is supported and where are we right now when it comes to Panther Lake?
Yeah. So since Panther Lake goes to many platforms, we had to add DDR5, and which is still valid technology for mobile. It gives more capacity, it's cheaper, somewhat more flexible with regards to board building blocks. So we added DDR5. This is the big thing, and I think Intel is one of the only that generates a combo PHY that has both LP5 and DDR5 on mobile. And this memory controller actually connects the two. It can drive LP5 technology or DDR5 technology, and it fits different speeds, each of them with the technology that exists. And we fitted the hardware to meet that. It's sometimes challenging because you go to high speeds.
Right.
So both it's challenging from PHY building blocks, building a PHY that goes to high speeds, as well as also have the memory controller deliver the bandwidth that this speed actually requires. So we had to support some gearing technologies and stuff like that, even enhance it further versus the previous generation that we had.
Yeah, because the thing that was very impressive is the speeds that you're able to achieve compared to Lunar Lake. Because for Lunar Lake, we were like, okay, the memory is on package. So there's a lot of savings, a lot of less issues that you have to deal from a technical integrity perspective. Yes. But now that you are trying to make it more broader for more options, giving more options to our partners, but you're still achieving higher speeds. So the memory is not, for Panther Lake, the memory is not embedded. It's actually, again, outside, but you're still achieving higher speeds than Panther Lake.
Definitely. First, when you switch from memory on package to memory on board, the amount of options you have are much bigger. So your verification or validation space is growing exponentially. So you need to validate to multiple type of DDRs, multiple type of speeds, multiple type of capacities. So it's a bigger space versus having something that is closer to the SoC. It's just few types, few capacities and speeds and you deliver the chip with it, validate it and all. In the memory on board case, you have to deliver a chip that works with many different configurations that you haven't even seen. And this is indeed challenging. So it's from regards to memory training,
right?
Yeah, and validating the speeds that actually work, and not only work functionally, but also have the right parameters with regards to latency and bandwidth, so they will be optimized from PNP perspective and for all the different speeds. We also, by the way, change speeds at runtime. So it has to be working up to a specific speed, but also in lower speeds. Good, because when you want to save power, you go to lower speeds, and when you don't need bandwidth, it's sufficient. And then you can lower voltages, lower frequency over the SoC, it consumes less power, and you gain from that.
When it comes to the evolution from Arrow Lake, from Arrow Lake to Lunar Lake, now to Panther Lake, how has the SoC power evolved in there, and how has it helped with or changed the performance?
Yeah, so we had some mindset when we were building Lunar Lake from Arrow Lake and then to Panther Lake. The mindset was efficiency first, performance later, while Arrow Lake was in performance with higher priority. So we took Arrow Lake and we said, okay, which are the different blocks in which we need to improve? The first one was improving the efficiency cluster, or what was called low power island in Arrow Lake. And we said this cluster has to be efficient in a way that it can run a lot of application. If you have a low power island, but it cannot be utilized enough, then you cannot gain in many workloads. So the first thing was actually making it more performing. And when we made it more performing, then we said, okay, so how we're going to build it to also be efficient. So what we did is, first, we took it from a 2-core to a 4-core topology.
Right.
We increased the cache, now it's more performing. The second thing that we did is we decoupled it completely from the system agent, meaning it was, from voltage and frequency perspective, it was decoupled. So you could, for example, have the system agent running on one frequency and this efficiency cluster running on the other frequency, which were coupled in Arrow Lake. This was the second thing. The third is that we also invested in the process nodes for this efficiency cluster. We actually moved it to the best node like we have for the performance cluster. All of those made it a very performing and efficient course, and we could utilize it quite a lot. So if you have casual loads that are actually running on something that is lighter and it's good enough from quality of service and from performance perspective, then you win. The other thing that we did was actually adding a memory side cache.
Oh, yes.
And this memory side cache can be used for any agent on the system, but it was very beneficial for the efficiency cluster. It actually gave it quite a lot of additional IPC. And while giving this additional IPC, it was also reducing the amount of memory traffic. So you gain both. You gain performance and you gain additional power. This was excellent. And we saw that this is increasing even further the amount of usage we can do with the efficiency cluster. Both concept remained for Panther Lake. So it's a carryover of the things that we do. We, of course, added internal microarchitectural optimization to both the cache itself, improved latency and things like that. So it made it even better. And for the efficiency cluster, we upgraded the core. Okay, so you get the additional core optimization into the efficiency cluster, you gain more. I think the thing that we need to think through the next generation is how to make this still performing but not grow in power, because you still want to maintain the performance, but you need to make sure that you're not growing in power. Otherwise, it defeats the purpose of this efficiency cluster. So we'll see how it goes, but so far it's good.
What is new on Panther Lake from a previous processor? So when it comes to the cores?
So, first we're in 18A, right? Intel's leading process technology. And so we rebuilt the cores in that process technology, right? We've got our next generation P and E-cores. Cougar Cove, that's the new P-core, and Darkmont, that's the new E-core. And so we took both of those and we built them specifically for Panther Lake in 18A. We changed lots of little things about them, to bring a bit of IPC. So we've got more prediction, we've got more cache, we've got a different structure, we've got a different core mix on Panther Lake, which is really, really nice. And that's just kind of the anchor that we're building for Panther Lake performance.
No, that's great. Actually, it's pretty interesting. And you're like saying nonchalant, we just shifted over to 18A, which is actually, that's a very big thing to do, move from one process technology to the other, because you have to recharacterize like transistors, metals and everything. So that is actually very big to move from one to the other.
Yeah, absolutely. So, with 18A, one of the goals Intel has is to be a good foundry. So from the CPU perspective, we tried to interact as, hey, we're a foundry customer. We need PDKs, process development kits, release schedules. And with that is a new library. With 18A, it's change how power delivery works on a fundamental level. That goes all the way through the library cells. That changed how we synthesize, how we built, how we route all of our signals. So yeah, that transition, every time there's a new process technology, there's a few new little tricks you have to learn and play. And so that is something we had to focus on. So especially with that backside power delivery. So again, that changes our library cells. There's no longer power routing in the library cells. Right. When you remove that, you can make everything a little bit smaller, so we get density out of it, which is great. It also helps voltage. So because we can dedicate more resources to power delivery, we lose less through the system. We lose less voltage drop as we go, because the resistance is lower. And then on the flip side, it also introduced some challenges. Right. So since I don't have power, when I route signals, I can't do what we call shield them, right? If I take a signal and I route it next to power, it's less noisy, less attacking. So I can't do that anymore. So we had to do different ways, spread things out, choose how we route them, et cetera. So it's just, it's different and kind of fun, and just another challenge.
Yeah, it's pretty interesting because back in the days when I used to design, shielding was very important on high frequency clock traces. You put power necessary just to make sure there was no crosstalk.
Exactly, that's exactly right. And so now, if I can't shield, what do I do? So, spacing is the answer, or you make the metal wider. That's another option, right? But yeah, it's keeping signals from attacking each other. And you still have to do that because you want your clock signals to be nice and clean when you route them through the design.
Yeah. Before the cameras were rolling, you and I were talking about like all the different changes that were done to the cores. Like they were like, oh yeah, there's like nerdy little changes, but I'm like, yeah, they're nerdy little changes, but they add up to make some great IPC improvements. There were some changes to the front end and the back end. Can you tell us a little bit more about those?
Yeah. So for example, Nanocode. Right. This is something we introduced in Skymont in our E-core, and this is our second generation. We're a little bit better at it now. So there's microcode, there's nanocode. What on earth is that, right? So microcode is typically a ROM. It's internal UOPs that we have so that we can do complex things, right? Power state transitions or complicated ISA or copying large amounts of memory. Typically, we will use microcode for that.
Right.
With our E-core, with this clustered front end, if you only have one microcode ROM, you can, if you need it all the time, everybody kind of has to wait and use that thing when it's your turn.
Right.
So what we did is we came up with a way to put small sections of microcode into our front end, into each decode cluster, so that we no longer need to go to microcode for those. So now if I've got 3 clusters, for example, is what we have, I can be generating 3 different flows all at the same time on all different clusters so that we can get ahead of the machine and always have the UOPs waiting for the back end. So we introduced it on Skymont. On Darkmont, we have more cases, we have faster cases, we just evolve over time and kind of get a little bit better at building it. And in the end, we've got instructions that used to go to microcode and now they don't, and they're compressed, and you just get performance out of it.
You get more performance because you're not waiting for that one to be freed on, so you can actually start executing.
Exactly. So it's parallel x86 decode, and now it's parallel x86 microcode execution. But we call it nanocode because it's a subset. It's not everything. We still fall back on some of the more complicated cases into the UROM.
No, that's pretty interesting. And this new whole architecture for Panther Lake, so we have the Darkmont cores, which are the E-cores. And then we have the Cougar cores, which are the P-cores. And we also have, just like before in a previous generation, we have a low power island right there. They're exactly the same, right? But there's like any differences from one to the other, like from the E-cores on the CPU compute and then the ones on the low power island?
Yeah, so in Panther Lake, we're a 3-way hybrid. Right. We've got this low power island that's our Darkmont E-core, and then we've got our P-core that's on the ring, and then we now have Darkmont's E-cores on the ring as well. So the implementation of the 2 Darkmonts, of the 2 E-core different places, is the same. Right, inside the core, it's the same cache, it's the same microarchitecture, it's the same polygons, really.
Right.
And but the functional performance behavior is a little different, right? So the ring is great for performance, right? It runs at a couple gigahertz, depending on where we're running it. It's a bigger cache, and so when you put a Darkmont in that spot in the system, it runs faster. I've got more cache at a shorter latency.
Right.
But there's a power cost to that, right? I've got the ring, I've got it on, I've got to have it running. When you put it in this low power island, then you don't get the benefit of the performance of the ring, but you get the power savings of it. So it has it has a different IPC, right? The performance for any given workload is different between the two. It's usually a little lower because we don't have that nice ring, but the power savings you get for that is excellent, right? We do have cache, we have system cache there. So that's the kind of example of, it's the same IP, built the same way, but you get different performance just because it's in a different context.
Okay, that makes sense. And we were talking also earlier, like it also has like different power rails attached to it, different power configurations, so you can actually turn it off.
Right, yeah, exactly. So we can turn off the P-cores and the E-cores. We can turn off the ring, and that's one set of power delivery, and we have ways to manage the power there. And then we have a separate power domain that we can use to on and off for the low power island. So in actuality, you could have any mix of them on or off, but you have a different voltage frequency curve for the 2 different places, and we have all that control in the SoC, again, to optimize that performance and battery life at the same time.
Right. And when we move from Lunar Lake to Panther Lake, now we have, I can't remember well, but I think we have a bigger cache now in those cells in the E-cores.
Yes. So the system cache is generally the same capacity, but on the ring, so Lunar Lake had 4 P-cores,
Right.
and with that, we each one sort of got 3 megs of cache to build a 12 meg LLC. Now that we brought 2 more E-core clusters, so 8 cores, we get an extra 6 megs. So now you got 18 megs in that ring. So that increases the performance of single thread for Cougar Cove, as well as that MT throughput. So it's a nice I love cache.
Yeah, I mean, cache is always good. And actually, we have that side memory cache in there.
Yeah.
Can you tell us a little bit more like how it'll work and who could have access to it?
Right. So the system cache is built to help the low power island, the E-cores.
Right.
The goal there is to lower the DRAM bandwidth that you need. So going to memory is power. It's a power expense, and so the less you do that, the lower power it is. So the low power island gets the benefit of it, but the other IPs can as well, right? So the NPU, the GPU, they have the ability to put data into that as well. Now, something like a GPU usually runs through a lot of data. So a cache of that size, you don't want to generally use it. But as long as in the software drivers, et cetera, you can say, oh, this small amount of data I want to hold there, then you get more of that benefit. And same kind of thing with the NPU.
Yeah, that makes sense. Yeah, so there will be like, because they're like hierarchy of who can access it and what makes sense, like which IP makes sense to be able to access it. Because like you were saying a little bit earlier, like for the GPU, it doesn't make sense because of the buffering. Like the information that they handle is a lot bigger than the size of that cache.
Right. Yeah. So streaming through, making a million triangles, et cetera. Right. That's probably not going to be effective. But it's a cache, and I think there are pieces that you will cache in that from all the IPs, and I think our hardware and firmware will make those decisions just to try to get that performance versus battery life trade-off again.
No, that's great. I mean, this is the architecture for this is mainly focused towards for mobile, for battery life and also performance, but a lot of things was done thinking in battery life.
Yeah, absolutely right, and that's the whole point of Panther Lake, right? Is bringing world-class battery life to something that can scale up and be your gaming laptop or whatever you want, right? And on the GPU side, we've got some great demos that I think everybody got to see that are, as a CPU guy, I think it's really impressive.
Yeah, it's pretty neat. So Panther Lake is like the culmination of this road that we have been doing, right? So we went from like we grabbed different things from like Arrow Lake, Lunar Lake, and Meteor Lake. Can you give us a little bit more or less like, oh, this is nice from this and this and this, and we put it all together?
Yeah. So Meteor Lake started the 3-way hybrid journey, right? And there we didn't put enough performance in that low power island, so it wasn't as effective, right? So the idea of a low power island starts there. Lunar Lake kind of brings that home and says, here we put a lot of performance. Panther Lake optimizes that, so we get a little bit more. 18A contributes. Right. So now you got this SoC that's just this really low baseline of power. And because the SoC is a low baseline of power, now when you bring Arrow Lake-like performance into it, you have more headroom. Right. You have more power available to give to the IPs. So, you layer that, now CPUs themselves get to use more of that power budget when you're doing CPU work. But the other thing that Panther Lake did that's really nice is we get better at the software and firmware every generation. And so the software and the firmware is contributing here as well. And now the CPU, we've got low power so that the GPU can take up the power where it needs to, because we've got this new really high performance Xe that's in the system. So that ability to balance it all up and down is great. So 18A gives us that efficiency. The SoC architecture gives us that power savings. Now we've got enough cores in here to give that really no excuses performance, and then we've got a great GPU. You put it all together, and this Panther Lake can do it all.
Panther Lake, as you know, we have new P and E-cores that are being introduced, new microarchitecture. Stephen has already talked about it, a lot of enhancements on IPC and increasing some of the buffer sizes, etc. So when that happens, what we do in Thread Director, if you remember in Thread Director, we have 2 components, right? One is the core classification. And in that component, we have different classes of instructions that we put them into buckets of, right? So that needs retraining. Why? Because our IPC changed, the ratios changed, and we have microarchitectural improvements. So definitely that is one of the improvements that we did in Thread Director, that retraining of these models to get new classes. The second one was we had new power management inputs. So there are power management enhancements that we have done with respect to, meeting platform intent from OEM side that they specify. And that in output, if we make certain decisions on which ones are performant cores, which ones are efficient cores, the decisions from that or hints from that get communicated to operating system via thread director. So there are some enhancements internally in the plumbing of that we have made. There's also, new kind of busy workflows that we have added in the training of the models and classification. Because if you look at your and my usage of IT or anyone's usage of IT laptops, right? Nowadays we are multitasking. There's some AI running on CPU. There is, another application running in background. I have 10 Chrome tabs open with different websites open. I'm doing productivity. All of this busyness causes our classification to be different from instance to instance. So we've added those use cases to be kind of more realistic aware in our training that we do for this classification. And last but not least, because we have these, compute P-cores, compute E-cores, low power E-cores, they all together provide feedback to operating system, right? Because they could be running different things together. And so the feedback coming simultaneously from all of this going to operating system, those are some of the enhancements that we have made in Panther Lake.
Oh, that's pretty cool. And like you just mentioned, we have different types of cores. So we have the low power E-cores, we have the E-cores, and we have also the performance E-cores. As we have evolved throughout the different architectures that we have through all the different hybrid architectures, the scheduling of the workloads has changed. We went from like going straight to the P-cores and then moving the workload to the E-cores, then to start it on the E-cores, and so forth and so on. How does it look now when it comes to Panther Lake?
Yeah, that's a great question. So if you look at before in Alder Lake and Raptor Lake, because of the monolithic design that we had, the E-cores were also on the ring, and we really didn't have a low power island. That time our goal was using E-cores for performance, right? We were using it for multi-threaded efficiency, efficient output for performance side. Now, since Meteor Lake, we started to have our low power island. And so we introduced an option with Microsoft to have scheduling policies of starting with efficient cores only, right? And when we say that, what it means is from thread director side, thread director provides an ordered list to operating system, which cores are most performant, which cores are most efficient. OS then picks whatever the configuration that it needs based on the scheduling policy that is set by operating system default, or if OEM overrides it through PPM package and sends it to operating system, right? So in Panther Lake, Lunar Lake and Panther Lake, what we did was in unplugged DC configuration, and in some cases AC configurations also, we basically say that start from most efficient cores. That means that we start from low power island, right? If we can keep the work contained there, so let's take like Teams example with even MEP, the Microsoft effect package running. Right. We can keep the work contained there. Our LP cores are also quite capable in terms of performance. So they meet the user experience demands needed by Teams to run a 720p video conferencing call and run the MEP in parallel and keep the work contained on low power island, so we can stay there. And if, let's say some productivity usage starts in between, so that our demand now exceeds, we need higher capability cores. Well, we have thread director feedback going in that here is now the most performant core, and operating system can take that output, input that thread director provides, combine it with its own goodness and move the threads around, right? So all of these things with flexibility that we get is what we see in Panther Lake.
That makes sense. You mentioned there that you have like an AC DC depending on if you're connected or not, power. But I think that there was mentioned also that like for Panther Lake, we have tried to make sure that they're a little bit more balanced when it comes to performance and efficiency to that.
Yeah, that's a great question. So one of the features that we introduced in Panther Lake was kind of this intelligent experience optimizer that we have. And what it provides is ability in balance mode. So if you look at like traditional OS sliders, the Windows sliders that we get, we have max performance, we have balanced, and we have max efficiency, right? If you look at it, they're somewhat kind of static. You can move between them while you're using the system because it's very easy. You can click on the power button and move them, but it needs manual intervention of moving the slider. And usually when you look at end users, maybe tech-savvy people like us can do this, but if you look at end users, they don't touch that slider really, right? So one of the optimization we did in our platform software combining with our power management is if we are in the balance mode and if our platform software enables the feature to do this, it automatically figures out that, hey, I need more performance now, so I go to the performance side of the setting, or I'm running more efficient workload, like I'm just doing browsing and scrolling, where I don't need as much compute power. It goes to the efficient side of the settings, right? And it does this dynamically. No tuning needed, no user input needed, anything. And with that, we were able to bring up our DC performance on work use cases like Procyon or Cinebench ST by about 19-20% or so, which kind of gave us boost, and we minimized the AC to DC delta because that's what a lot of our customers are looking for.
Yeah, a lot of our customers, a lot of people see like, okay, they see the difference, like you said, the delta between the performance from between AC to DC, because once you're in DC, you're more focused on battery. Because you want to make sure that they extend, so you can work on that on the AC. But that's pretty neat. When it comes to our partners, in previous platforms, we were able to provide them with a type of a software or some hooks that they can actually use to set the system, the overall platform, to like the performance savings, or do we still provide those type of hooks?
Absolutely, yeah. So we do have the platform intent that we consume from customers, right? Our value-added software, which is Dynamic Tuning Utility, DTT, that provides an interface where our customers can choose the gears on which they operate on. We call it gears. There's a performance gear and there is an efficiency gear, and in between there's a spectrum, right? And depending on their designs, they can choose which point on the curve they want to stay at. So OEM X might say that, hey, I have a smaller battery capacity and I want to provide larger extended battery life. I might go more towards efficiency gear. Or another OEM might say that, hey, I'm doing a gaming laptop. I want to be more in performance state. I have a bigger battery capacity. They can choose more performance gear for that, right? All these gears then get communicated to SoC via an interface that we have built starting Lunar Lake timeframe, and we have expanded that interface in Panther Lake. And so our SoC gets the intent of, whether it's maximizing efficiency or maximizing performance. And accordingly, we take internal power management decisions on how to allocate resources, how to ramp up frequencies, do we need to look at anything else while allocating budgets between different operations? So all of these things kind of come from the input that we get from customers. So at the end of it, we get more, greater experience for customers based on their intent that they choose for their platforms.
That's great, because when we listen to our customers, trying to meet their needs, and also it gives them more flexibility of, depending, like you said, what type of platform or type of laptop they're designing to. Are you doing a thin and light to make sure that you're maximizing that battery, or you're making a gaming one which you're looking into performance?
Absolutely.
What for Panther Lake, what was one of kind of the most challenging things that you encounter and you kind of guys have to overcome?
Oh yeah, it's a great question. Yeah, I mean, every step of the way, as we kind of add more and more enhancements, there's kind of coordination between the different things and areas. This intelligent experience optimizer that I talked about, which kind of taking platform hint on what points do I want to choose, and then figuring out in SoC how I make that movement transparently was quite interesting. I mean, not from just communication across multiple groups and other type of perspective, but also what durations do we choose, right? We want to make sure that we don't lose on any user experience, responsiveness, snappiness, and things. But at the same time, we also want to make sure that the energy cost also doesn't go through the roof, right? Because on power use cases, we want to stay low. So I would definitely say that was one of the things that, it was great kind of working with everybody, designing all of that and bringing it to the ecosystem.
We've been developing graphics here at Intel for 20 years, or more than 20 years.
Right.
But recently we've really doubled down our investment, and our first architecture in our double down was called Xe. And Xe was a giant evolution of our graphics architecture, much bigger, much wider, and it uncovered a lot of things that we could do better in terms of our software efficiency, because we're, for the first time, shifting our load from being CPU limited to being GPU limited. We're getting much higher performance. And it showed up a lot of things we could fix. Well, that led us to Xe2, which we launched with Lunar Lake and Battle Mage. And that was our first real success. Lunar Lake was well received. Battle Mage had great reviews. I play games on Battle Mage all the time. It's a fantastic design. And we brought a little bit more balance to the graphics market. We improved our IP, and we set ourselves up for the next gen. That's Xe3, which we just launched. Xe3 is pretty cool. We've improved efficiency. We've made caches improve better. We dedicate more area to graphics. So for the first time, we're building the largest integrated graphics device at Intel ever.
That is awesome. Yes, because we have added more cores, right, to this new one.
Yep, we're up to 12 Xe cores. So we've gotten wider, and each of those Xe cores is actually more efficient. We've added more caching. We do lots of optimizations internally. So our net result is about 50% better perf per watt, which is huge. If you think about, gen on gen, 50% is crazy big.
Yeah, this is a great improvement. And also you did some changes to the XMX extensions?
Yeah, we've added a few more data types. We're doing a little bit more optimized register allocations. So our XMX units are getting even faster. And those are critical. We added support for something called cooperative vectors, which is sort of a joint effort with Microsoft. And what it does is it standardizes the way that game developers or other developers can access matrix multiply hardware inside of GPUs. So it works across vendors. So no more like CUDA specific stuff, or in our case, Metal kernels, or in AMD's case, ROCm stuff. At the end of the day, you can have a standardized shader that runs on all hardware, and it'll make AI much more accessible to normal game type people.
Yeah, because we have different things when it comes to AI for the GPU, right? Like one of the technologies that we have there is we have XeSS, and how's it evolved?
Oh, XeSS is cool. It's one of our very first times that we used AI for graphics. And what our first XeSS did is it took a smaller resolution image and it used AI to blow it up and make it better quality. So we got higher performance and higher fidelity. The next step was XeSS2, where we added the ability to do frame interpolation. We would generate, a smaller image, scale it up, and then use the next image and calculate the middle image and generate it. We call it frame gen. So XeSS2 added frame gen. And today, we just talked about our next generation stuff on Panther Lake, which is going to be XeSS3, which adds support for multi-frame generation. So instead of generating one frame, we can now generate up to 3 frames between 2 rendered frames, and it looks fantastic. It's got great performance, and it really shifts the balance kind of away from the graphics card, because we can generate now so much more frames. We're unlocking performance. When you turn on multi-frame generation, buttery smooth. It's amazing technology.
Actually, yeah, I was playing that because I was getting it ready for
Yeah,
the demo.
yeah, it's crazy, right?
Yeah, it's pretty
so
insane.
I think that's the way technology is moving us. It's going away from what I think of as traditional raster, much towards these newer sort of neural-oriented algorithms. And XeSS3, while it's really cool and it's a dramatic step forward, it's still just a baby step. And what you're going to see is dramatically different ways of rendering that we haven't even thought of yet. I showed a demo today called NERF, and it's a neural radiance field demo. And what it does is says, get rid of geometry, get rid of textures. And instead of that, what we need for traditional raster, we're going to have an AI model. And the way it works is I train that AI model with pictures, just kind of like imagining I'm shooting rays through pictures.
Right.
Then you know the color because you're shooting it through the picture. And you use that as training data to build this AI model. So that at any point I can insert the model into a game. And if I shoot it with a ray, it will tell me the color that it should be. So there's really no geometry inside it. It's just a AI model that we're interrogating, much like ray tracing.
So that I guess that brings down all the extra work and power you need to do to generate that, and it just makes it a lot easier.
Yeah, and that's a look ahead of a completely different way to do rendering. That could be the way things just sort of go. Someday we may not raster. We may actually just ask the AI model what the picture is.
Right, and like we have like rasterization, then we have super sampling, and we also have there like ray tracing, all these different things.
Yep.
So there has been an improvements too.
Oh
right?
yeah, all different techniques, and we're improving all of those on Panther Lake as well, right? So our raster gets faster because we're wider. So for traditional rendering, we're faster. For AI, we're faster because we're improving the way we use our XMX, and overall, it's good for everybody. We deliver great experiences for gamers.
No, that's amazing. There's some other ways in there that you were talking, or that you're going to be talking, when it comes to like gaming at low power.
Yeah. Low power gaming is critical, right? New form factors, handhelds, laptops, people want to be able to be untethered when they're gaming. So, by being wider, we can actually lower the power, and at the same power, we would deliver twice the performance. So it's this whole, more attention to platform level optimization. We have a new technique inside of the driver called IBC version 3. And what that's doing is platform tuning between the CPU and the GPU. It says, if I'm playing a game, then I know that I want to sort of have my GPU fully saturated. Right. So I'm going to shift power to the GPU, and then I'm going to give hints to Rajshree's thread director. We talked about this. So we have some scheduling hardware that picks E-cores and P-cores and how to do that. So now the GPU driver tells that logic, hey, we're playing a game, so please don't change things very often and favor E-cores over P-cores, and maybe turn the P-cores off entirely. So it's an amazingly smooth experience, and it lowers the power on the CPU cores so that we can add power to the GPU cores and get higher performance overall.
Yeah, that's amazing. And one of the things that we want to probably call out is like the E-cores, even though they're coefficient cores, they have improved so much that actually they'll be able to handle all the gaming.
Absolutely. And when you're more GPU limited, you tend to have more idle time on the CPUs anyway. So it's better to run that on a more power efficient core.
No, that's pretty impressive. There has been also some changes that you guys are bringing over that you have learned from, I think it was from previous platforms. Like I think it was like power and jitter and all that stuff on the loading.
Yeah, that's the same thing. So when you looked at where we were with Arrow Lake or Lunar Lake when we launched, we actually had a device built called the MSI Claw. And you remember the Claw, right? And it was really cool. I first saw it, I'm like, this is amazing. But as I was looking at it, I'm like, when I'm playing a game, there's a little bit of hitching here.
Right.
And it shouldn't be happening because we have plenty of headroom, we have plenty of performance. It should have been buttery smooth. But we didn't get that device till late into the development effort. And it was exposing some of these inefficiencies that were happening at our low-level power management algorithms. And that's where IBC came from, primarily for the Claw.
Right.
And it says, oh, wait a second, when I'm playing a game, just everybody chill. Let's not be not be swapping power around quite so often. Maybe keep more power on the GPU and throttle down the GPU slowly. And that algorithm dramatically improved the performance for Claw. That's why it sort of got a second review cycle and everybody loved it. And we kept working on that technology. And that's what you see now on Panther Lake.
Yeah. So I mean, this is the improvement, and I can't wait to see like if there's going to be any handhelds in the future. So it's going to be.
There are definitely going to be handhelds in the future. I mean, I don't know for sure, but I mean, it's such a cool form factor, right?
I love it. Yes, and that's my traveling gaming now.
Yeah, cool.
It's easier to pull out than just pull a laptop and
I agree.
Things.
Yeah.
All right, so we cover pretty much like on the side of the GPU. Let's talk a little bit more about the NPU.
Okay. So we have a new NPU, NPU 5.
Yes.
You could tell it's one better. And what we're doing there is we found with Lunar Lake that this whole move towards agents and generational AI for PC clients is accelerating. And we needed to find a way to bring that same NPU performance down our stack, which means that we can't afford to have a gigantic NPU. We need to find a way to make it smaller.
Right.
So that's what NPU 5 is mostly about. It's about doing area efficiency so that we can afford to make that NPU go everywhere. And that's what Panther Lake is.
That's pretty impressive. Smaller, it also means like less power.
Yeah, less power, less area, less cost. And now all of a sudden, you're going to see millions of PCs that are enabled with this versus a smaller segment with a bigger NPU. But we've also done other microarchitectural improvements. We've moved some things that used to be programmable things that would take a long time running on our DSP. We've added hardware into our neural compute engine to accelerate that natively. So things like supporting a piecewise linear activation function used to be more often run on the Shave DSP. Now we can run that directly on our neural compute engine using a programmable lookup table. It's things like that that are smart, going after pieces of inference that were slow on our prior generations that are now fast.
Yeah, there are also some changes. Like first we have like specific, I think it was a math function that will help us figure it out, but now we have more options, right?
Things like, if you think about inference, there's always an activation function at the end of every layer, and different activation functions are used in different types of networks. Some common ones are tangent and sigmoid, which are these funky, transcendental curve things. And there's no real easy way to implement those in hardware. So we basically punted those. And when you have any of those functions, you would need to kick off a DSP and run thousands of instructions. Now what we've done is said, we can do this better. So we put, I think it's a 256 entry lookup table where we effectively can create any transfer function for an activation curve. And so we can run that stuff directly inside of the engine and not doing effectively an exception path.
No, that's pretty impressive because at the beginning we only had the ReLU, right?
Yeah, we had leaky ReLU, we had ReLU. Now we have programmability that keeps all of the activation functions inside the core engine.
So it's great because I think that will help us, depending on the model, or be more open to different models.
Absolutely. Yeah, and as things, inference and model development is evolving at a just ridiculous rate, and to keep up with that, you need programmability. You cannot just hard code a particular type of neural engine because it's going to be good today, but it won't last. So we really focus on building a programmable engine that's optimized for inference but can tolerate variation.
No, that's great. There was a demo that you did that I really liked. It's Super Builder. But what is the proper name? It escapes me right now.
Well, we have Super Agent, which is the agentic component of Super Builder.
Yes, and this is part of the whole agentic.
Yeah, it's part of the whole agentic thing.
Maybe let's step out a little bit. What is agentic?
Agentic AI is the biggest change in AI, and AI is just evolving so dramatic. Agentic AI is when things start getting useful. Mm-hmm. So we've had a lot of toy applications generating faces and removing backgrounds, but they're not life-changing. Agentic AI is life-changing. And it's because what we've done is we've started to learn how to use these large language models to take action and interact with the world. So instead of generating something, now the way to think about it is give your model input, tell it that it's an agent. Right. Tell it that it has got an objective. And then these large language models can actually generate action plans. And then they can talk to other agents who are more specifically targeted, and they can generate interaction with external tools. So what this means is that you can effectively imagine PCs that you talk to, and they are more effective than, say, a personal assistant. They're more effective than your banker. They're more effective than your broker. And as this technology evolves, you will see much more ubiquitous agentic AI workflows.
No, that's. I can't wait to.
Yeah,
to be there.
I think honestly, this is the biggest change we've seen, and it's probably going to be bigger than anything else that's happened in our lifetime. And so that means that all of the work that's happened with deployment of large GPUs and these training of huge models, we want to be able to run those on our PCs. Right. And that's really what Microsoft is doing. That's what we're doing. And it will change fundamentally the PC experience.
And we're actually providing the tool that we just talked about, which is that,
Yeah, well, this Super Builder is available to OEMs who want to build agentic workflows for their PCs. And it's pretty cool. You can play with it. The basic idea is the way it works. Large language models are very good at predicting the next word. So you give it a sequence of words, what we call the context, and then the model has been trained using all the internet sentences, and it says, given this sequence of words, what's the most likely next word? That's really all they do. They're just predicting the next word, but they're doing it in such a way that it builds a reasoned conversation. And it uses an internal architecture called transformers to effectively understand semantic meaning from word sequences. And now the next step is this agentic workflow. And all it is shocking, is let's get a better context. Right. So as contexts are getting bigger, which is the input to these LLMs, you're not just saying what color is, where does the purple color come from? That would be a simple question, and an LLM could tell you the answer. Now you would say, instead of what colors, what's in purple, you would say, you are a helpful assistant, and I want you to evaluate the needs of the user, be ethical and be honest. And then I would like you to use these tools. You can query Google and he'll tell you answers. You can use this service to access flight information, and your user's request is blank. Right. And what the user does, he comes up and says, I'd like to make air tickets to Air France to London. And that whole string gets appended and stuck into an LLM. And now you're agentic because the LLM knows the tools, it knows its function, and it knows the request of the user. So it will generate text sequences that are activating tools.
Right.
It's really amazing.
Staying kind of on the AI subject, like we're trying to bring all these models, right, for different reasons into the edge, into the PC. There's different things that need to be done to do that. One of the things is quantization, but you can tell us through the whole
the quantization flow. Okay, so when you get a big new model, maybe Meta or OpenAI or Google or somebody has been working on it for years, and they finally say, "You're welcome, world. Here's a new model. It's ChatGPT 10." And it's a bunch of numbers that are usually floating point 32-bit wide. And the model might be next time 16 billion or 32 billion parameters, right?
Right.
So that's a big thing. And so how do you execute that on a smaller PC? Well, the key is you have to be intelligent about reducing the size of that model. And we use a process called quantization. It's a fairly standard thing. And what we're doing is trying to figure out which segments of that model can be reduced without losing accuracy.
Right.
So instead of doing 32-bit floating point, maybe we can do 16-bit floating point. Instead of doing all of these activation labors, maybe we can look at the ones that are very small and just drop them. So there's lots of techniques that have been developed over the years to shrink the size of these models without losing accuracy. So what we do is we have a tool called NNCF, which is our neural network compression framework. And that's where we bundle up all of our quantization tools. But we've also used those tools directly on the 300 most popular models already out there. And we've put all those optimized models on Hugging Face. So if you're sort of a developer and you don't want to go through the quantization process, we have pre-quantized models available for everybody. So the second step is you're a developer, there's a giant model, maybe you're doing some fine tuning and you want to quantize it, you can use NNCF and DIY your own quantization. Right. The third step is if you don't do any of that, we have logic inside of our runtime, inference running on the PC, that will do dynamic quantization in real time. So it's looking at, maybe if I try running this 8-bit instead of 32-bit, it'll be okay. And so as it iterates through the AI models, it's actually quantizing it and shrinking it down.
No, this is pretty impressive. There's a lot of different things that are going on.
There's a lot going on here, Alex. It's crazy. And AI is the most important thing I think that we have to focus on for client and for our data center products.
Yeah, it like you said before, it's impressive how quickly we're like I'm having a hard time keeping up with it. So it's fast.
I'm having a hard time keeping up with it. One thing I do want to mention is we have a group inside of Intel that is named OpenVINO. And a lot of people get confused because OpenVINO means a lot of different things. Yes. We have an API that is an OpenVINO API where people can code up applications that directly use our engines, and that we call OpenVINO. We also call our runtime, which is the piece of code that always runs independent of whatever API you're using. That is called the OpenVINO runtime. And what it is it's like an inference engine that we do in software. So all these different software stacks call into our OpenVINO engine, and that executes on our different IP. So if we have a GPU or an NPU or a CPU, that OpenVINO inference engine is picking the right core and doing the optimizations. So the cool thing is, that thing is getting better and better every day. And they have different technologies. They've got a roadmap that goes on forever. So all the different optimizations that we do on OpenVINO runtime accelerate AI no matter what framework or what API developers are working in, including Microsoft. Microsoft just announced something called Windows ML. Yep. And Windows ML is their standardized way of doing models. It's based on Onyx. And we've been working with them very closely for years on this, actually. And now going forward, you'll see AI developers on the PC platform using Microsoft standardized multi-vendor agnostic platform. It's really cool. No, that's great. All accelerated with our OpenVINO runtime.
That's impressive because the accelerator, it kind of sounds a little bit like the threat director is like, okay, we're going to use this type of.
Yeah, I mean, it's similar. It's basically providing an inference API so that different companies don't have to try to figure out how to use how to use all of our DNN stacks and how to use our communication stacks and how to use open compute stacks. They just know inference, and everybody does it the same way.
So basically, IPU is an image signal processor, which is integrated within the platform SoC.
Nowadays, images and video has become very relevant, but can you tell us like how embedded, because I didn't actually realize how embedded it is in our life until I actually was talking with you earlier and kind of looking at different presentations. So can you give us a little, taste of how embedded it is into our culture nowadays?
So basically, up till COVID, no one actually knew what the webcam is. No one opened the webcam, or it was kind of a solar eclipse event when you did that. That's why no one cared about it. So basically, by 2020, you had 720p cameras, very low performance, very low quality. No one cared about it. And then came that day with COVID. Suddenly, you open your device. You wanted to open your camera, and you ask yourself, "What is that?"
Is that me?
Yeah. So, colors are washed out, a lot of grainy artifacts, a lot of noise. Basically, a complete different image than what you're used to in your mobile phone, right? So on one hand, you got mobile phones with top quality. On the other hand, you got mobile PCs, and the quality is not even close. So that generated kind of a bigger trend to kind of catch up with the mobile phone world. And since 2020, we can see much more recognition in the need for good imaging in a mobile PC. And we can see the trend of cameras upgrading from 720p now to 4K in premium devices, and let's say 5 megapixel 1440p for average devices. So that caused a huge upgrade throughout those years with better understanding of what is the camera, why we need it. 20% or 22% out of the US workforce is working remotely nowadays. I think another 20% is hybrid. And even when you go to the office, you go to a conference room and you open your device with the camera and you have someone that's remotely connected talk with you. So basically, I would say a huge percentage of the market is using actively camera on online meetings, and it became as critical as using your keyboard.
Yeah, it's definitely, after COVID is like before and after when it comes to the demands for cameras and also the camera quality and the different things that comes with it. One of the things that I was looking at is just not like one camera. There's like, you have the lenses, then you have the sensor, then you have the ISP. Can you tell us a bit more of how does that construct work?
So a camera system is actually built out of several components. You have your camera module at the top of the device, and it's composed usually out of a lens system, meaning multiple lens. If you have a discrete ISP, then your discrete ISP is going to be up there after those lens systems and sensor, and probably some communication method, whether if it's USB or MIPI, to deliver the data to the system.
How common is to have that discrete? Because I was looking at the data and I was actually surprised to see. I look at the benefits of having it integrated versus discrete. And I was like, why is it discrete? I mean, why not make everything integrated? If it has so much improvements of discrete. Question.
First of all, I think that discrete has been there forever.
Right.
So it gained market momentum throughout the years, and it became a very cheap commodity. While integrated ISP, while it's cheaper in terms of the ISP itself, the system itself, implementing the system with the more expensive cabling, MIPI cabling, has required more from the OEMs. So it became a premium kind of upgrade.
Yeah, I guess when you say like the cabling and all the routing of the thing, it has to be very different from the other one, because I think you were saying it was like MIPI or USB, which is a little bit like cheaper to route and
so
more forgiving.
USB fits, yesterday's needs.
Right.
For 720p, you can get that with 480 megabit per second, while MIPI fits more of the integrated ISP needs for high resolutions processing. So MIPI can get you up to 6 gigabit per second.
No, that's impressive. Okay, so now we have the ISP embedded into Panther Lake. What are the kind of the new features that we can expect from that?
So we got 3 features on Panther Lake, 3 new features. The first one is staggered HDR in hardware. Basically, it's the ability to merge 2 different exposures, high exposure and low exposure, merge them together in order to get wider dynamic range. So that's more for HDR capabilities, giving us, if we look at the outdoor scene, you get very clear sky, blue sky. We're going to see you very clearly. We're going to have all the details and all the colors while having a wider dynamic range. And we do that in hardware now, comparing to previous generations. And that provides us with better power saving, up to 1.5 watts, and of course, better performance.
So what was previously doing at a software level? And
Yes.
then, okay, but now it's doing at the hardware, so that's why you get all these gains from that.
The second feature is AI-based noise reduction, which is very interesting. So AI-based noise reduction allows us to actually kidnap the raw data from the sensor, take it to the memory, and then pass it to other compute engines like the NPU, where we run specialized neural networks that actually do noise reduction in the Bayer domain. And that means in the raw Bayer domain. Okay, we haven't done any processing yet.
Even before it gets to that.
So it's very efficient to reduce noise specifically for low light environments. And then once we complete that, we shift it back to the IPU and finish the processing. That allows us to have amazing result for low light environments. And that actually one of the advantages for integrated ISP. So when you're with an integrated ISP, you have a flexibility that you don't have in a discrete ISP. So you can do processing before the imaging pipeline. You can do processing in parallel to the imaging pipeline and get to and off the pipe. And you can do post-processing. While in USB or discrete solutions, you can do only post-processing, because once you've done your processing, you can get on and off the memory and get it back to the ISP. So once you finished with the processing, you compress your data, you ship it, that's it. So anything else that is done post-processing on that compressed data is less efficient
than the raw,
than the raw. This is one, so the image quality is going to be degraded. And of course, efficiency and power won't be as you do it integrated to the system.
So the algorithms are created in a neural network, but then we have that algorithm implemented in the GPU that is able to teach them to do all the denoising. So that means that denoising can get better with time, because if you update that algorithm, then it's going to be a lot better.
Of course. So as we work generation to generation, we continue to do upgrades in the pipe, whether if it's image quality or other performance, other than the new stuff that we offer to the market.
Right. Okay. So we have those two. What will be the
So the third one is called AI local tone mapping. And local tone mapping basically is a process that allows you to adjust brightness and contrast per pixel in a better way. And that better suits HDR scenes, where you have wide dynamic range, you have a wider dynamic range for your brightness, and you need to compress it for traditional displays. So with that LTM, local tone mapping, we're able to provide better details, better contrast, better blacks, and it really complements our staggered HDR capability.
So I was also looking at also kind of helps with light artifacts, which was pretty interesting to see, like the one, before and after. The before you see like it was just like RGB, like 3 different colors, but then after the correction, it's just like, no, it's just white, which all the 3 colors make white, but you can actually just see it as white. So it was pretty interesting to see that.
So usually in traditional methods that are implementing local tone mapping, some of the problems can result in flickering across frames because it's temporal. Some of the problems can be halo artifacts. You see those halos across different edges. And with our LTM, which is AI-based, running on the NPU, you simply don't experience those.
I also see that it was called out that it supports 3 cameras. Does that mean that you can usually have 3 lenses or 3 different cameras? And how did that work?
So you have different type of devices. Let's start with clamshells. So with clamshells, you can have 1 camera. You can have 2 cameras. So 1 camera is RGB and 1 is IR for win or low, which is very common today. And for some devices like 2-in-1s or tablets, you got also a world-facing camera. So we're able to support all those use cases just with 1 ISP and not with 3 like others.
That's pretty impressive. I mean, that like power savings and be more efficient.
And of course, it's up to 16 megapixel per camera today. So that means it gives you a lot of flexibility with choosing your sensor from very high quality ones to traditional ones.
Yeah, because depending on what type of device you want to create, you can go for very high or very low. Is there a specific? I guess there should be a specific handshake between the sensor and the ISP.
Yes. So basically, a sensor driver, let's say, is combined out of the sensor driver and the ISP sensor, the ISP driver. So both together are part of that package.
Okay, that's pretty impressive. For this, what was the most challenging thing that you run into trying to implement all this on Panther Lake?
So it's not necessarily only for Panther Lake, but for all of the integrated ISPs. Sometimes it takes a bit longer in order to implement and integrate the camera stack, comparing to a shelf product. So we'll need to remember that this kind of integrated ISPs, they are not considered to be a shelf product. It's not a plug and play product.
Right.
So it's a joint venture with the customer or with the OEM, where we decide together, what's going to be the sensor, what's going to be the lens system, how it's going to work, what's going to be the spec, and then we integrate it together. And we need to integrate the entire stack together. So it takes a bit more time than traditional plug and play, but it has its advantages as well, because you get what you design, and you design, your own solution that is unique and differentiate, and you're able to differentiate yourself from the others in the market.
No, it's pretty amazing, because I mean, it makes sense now that it's such a heavy lift. If you want to create like a top of the line product, you have to work so closely to make sure that the camera they're using, the sensor lens, the sensor chip is also compatible, and you make sure that everything comes in together. So it's pretty impressive.
It's not that bad, because you do it only once, and then you scale on your different product lines.
Oh, okay.
Right. So you have your 1 or 2 design wins that are selected, working and great, and then you can implement those on the rest of your devices.
I think you said that it also was able to correct for like lens issues with the camera.
Well, basically any ISP, one of its initial functions is to correct any lens aberrations, vignetting, and sorts of distortions that comes with the lens or because of the lens system. So these are part of the initial actions that are being made in any ISP.
So you said there was one more thing that you wanted to know about the AI.
So today devices are becoming more challenging, because we want to have new and exciting form factors. So cameras for new and exciting form factors reflect in a way that, it's like cameras under display, or small cameras that allow you small bezels, thin bezels.
Right.
And basically each one of those things comes with its own lens limitations, right? So a camera behind the display is being blocked by the light. So it's in constant low light condition. This is exactly where the places where you need an integrated ISP, because then you can first process bigger, higher resolutions, right, that will provide more quality. Plus, we can enhance it with AI to provide better noise reduction. And for small cameras, on slim bezels. We just provide better performance. So if you have a 1080p small camera that is limited, it doesn't mean that it's going to be lacking, because if you're going to use integrated ISP, you'll be able to get 20 to 30% more in quality.
And that's because you're able to grab that data, that red data, before it reaches the ISP, process it in the GPU, and then bring it back and do the
Exactly.
We have talked about Wi-Fi 7, right? But then again, here in Panther Lake, we're going to have, there's a new version for Wi-Fi 7?
Yeah, so Intel, we actually launched Wi-Fi 7 at the end of 2023. That's when the Wi-Fi 7 certification came to market. This time around, we're actually launching new features, so what we call usually Wi-Fi 7 Release 2. So we have now new capabilities that we add into our Wi-Fi 7 product that are going to make it more efficient, lower power, and with much better quality of service for many applications.
Right. So we were talking about a minute ago, the different capabilities. And one of them that we're talking about is, I think, multiple devices. I think you can correct me. I was referring incorrectly as MIMO, but you correct me. But it's actually, the name of it is multi-link operation.
Yeah. So this is the flagship feature of Wi-Fi 7. Okay. If you ask anybody, what is Wi-Fi 7? What is the main feature? That's the one. So what multi-link operation does is really extends the concept of MIMO now to, if you think about it, it's almost like taking the multiple antennas we have on the platform and allowing those antennas to be on different channels. So what we call, that's why we multi-link, because we don't use the term channel, we use the term link because it's a more generic term.
Right.
But you can think of it as being a channel. And that channel can be in any of the frequency bands that Wi-Fi operates. Today Wi-Fi operates in the 2.4 gigahertz band, the 5 gigahertz band, or the 6 gigahertz band. And so if you have a client device like a laptop that has two antennas, it can essentially place one antenna on one channel, say in the 5 gigahertz band, and another one in another channel in the 6 gigahertz band. Essentially what we are trying to do is to increase the chances, right? Improve the statistical multiplexing, and to increase the odds that, whenever you have data to send, or whenever the access point has data to send to you, it has to know where your antennas are so that it can trigger you, so that you can go from this single antenna, which is not a very high performance mode, but again, you're just trying to connect the device, and then go from a SISO, a single antenna, to a MIMO mode, and then perform the high performance communication after that.
So they're is it constantly probing those different band frequencies, or the channels within the band frequencies to do that?
The way it's not constantly probing. So the way it happens is that, if I'm a client, I start operating a network, I tell the access point, say, look, I'm now entering this multi-link operation mode, which we call in EMLSR, Enhanced Multi-Link Single Radio. And I tell the access point, and I say, look, I'm going to be listening on, say, channel 6 and channel 57. So the access point will know. At that point, whenever you're in that mode, well, two things can happen. Either the clients are going to have data to send to the access point, or the access point is going to have data to send to the client. If the access point has data, it knows where the client is listening.
Right.
So it just sends a short packet to tell the client, I'm going to have data for you. And it's going to use whatever channel is available first. At that point, let's say that it sends a packet to the client on channel 6. Whenever the access point says, I'm going to send you data on channel 6, at that point, there's a handshake, and the client moves that antenna that was on the other channel to channel 6 and says, look, now I'm ready to receive data from you at high performance now, because now I have both antennas. Likewise, from the client side, is simpler, because the client knows when it has data. So if it needs to send data on channel 6, automatically it's going to go into a 2x2 mode and send data to the access point. So it's not constantly probing, it's based on the traffic, right? Based on data that's going to be exchanged, and that's what triggers on demand, moving from one link to the other, your antennas.
So about your example, does that mean that two devices can be kind of the same channel, and they could just be waiting, and that way one waits, the other can send, though, or
Yeah, the way that Wi-Fi operates, because it operates on this what we call unlicensed spectrum,
right,
is that it's a contention-based access, which I think is what we're referring to. So if you have one access point, we have here multiple client devices associated with the access point. If they have data, they're all going to contend for access to the medium.
Okay.
Right. So there is a possibility that maybe you're going to be on a voice call, you have a packet to send, but another device just grabbed the channel. But you need to send that packet, right? So what this multi-link operation does is, well, if somebody grabbed the channel 6 and I cannot send my packet now, well, but I'm listening also on the other channel. So I can move my antenna to the other channel and be able to send the packet, right?
And that way you don't have to wait and actually have
that way you don't have to wait, and the voice quality gets bad, and the user gets frustrated.
Yeah, with the drop packages with the robotic voice and everything like that.
Correct.
Nice.
Yeah.
So that's a pretty cool feature. There's another one that we're talking about that it's more about like the application getting access or privileges to get it to the access point, depending on the urgency of they have to send the packets.
Yeah, absolutely. I mean, we call these, the technical term is, we call it restricted target wake time. So target wake time, because this was done also as a power saving means. So the idea here is you're actually able to negotiate with the access point the periods of time when you're actually going to have data to send. So this usually works if you have periodic traffic.
Right.
So if you think of video or voice, usually these are periodic traffic. And so the idea here is that if you know that you're going to need access to the channel every 40 milliseconds to send a packet that is, say, 2 milliseconds long, you could tell the access point and say, look, I'm gonna need to send every 40 milliseconds a packet that is 2 milliseconds long, and through that negotiation with the access point, if the access point agrees with that, basically during that time you're going to have restricted channel access. So if there are other clients on the network, they're going to be quiet during that time because they know that you're going to. So even if another client has data to send, say, look, this time is reserved, I cannot use that time.
Well, actually, that's even better because like sometimes in events like this, there's a lot of so many signals or Wi-Fi interference trying to communicate. So that will make it a little bit cleaner to be able to communicate.
Yeah, absolutely. I mean, I think look, the thing with wireless is that it works perfect until we have a congested environment.
Yeah.
Right. So a lot of the things that we try and do is to make sure that it continues to work perfect as best as we can when you have congestion, when you have interference. That's the challenge. Because if you're in an isolated home, all the channel is yours, so most likely everything's going to be okay. But if you're in an environment like this with so many people, everybody using their laptops, their phones, everybody's connected to the access point, how can you make sure that when that happens, that the channel is loaded, that you can still prioritize traffic, right? And so what we are bringing with Panther Lake is the ability that users can, if they have traffic that needs to be prioritized, that they can negotiate with the access point. And by having the negotiation in your Wi-Fi on your laptop, it's still going to work well.
There's another feature, I think it's called, is it peer-to-peer connection? Does that mean like peer-to-pear right there?
Yeah. So, I mean, let me explain through an example because I think it makes things easier, right? I mean, here in this, in the event, for example, we're going to have a lot of people taking pictures. Right. And then when they want to take a picture, and they want to transfer that picture to their laptop so that they can post it, they can do something. That connection, that sending the picture from your phone to your laptop, it doesn't have to go through the access point. It's something that can go directly from the phone to your PC. And that always going to use Wi-Fi because that's the fastest means to transfer the content. Now, the problem is that today, there is no coordination between the clients that are going to be sending and receiving that picture and the access point. They say, which channels are you going to use? And most times, actually, we see this all the time, is that clients, I'm connected to the access point, and at the same time I need to transfer the picture, I don't even bother to change the channel. I'm just going to use the same channel. And that causes interference with all the users of that channel. Oh. So if there are other clients that are trying to have a voice call or do other things, I say, look, I don't care. Yeah, my laptop is here, my phone is here, just close by, so I'm just going to use the same channel, and that causes interference to the access point into the infrastructure. And so what this feature does, we call it this peer-to-peer channel recommendation. The idea is the access point now is going to have the ability to tell the client, look, if you want to do peer-to-peer, I'm going to allocate some channels for you to do that, right? And so we've been working with enterprise vendors, for example, to make sure that in enterprises, whenever we want to do, whether it's transferring files between laptops or whether that is mirroring your screen to a big screen, that we're going to be using channels that the access point tells us to use, so that at the same time we can optimize that peer-to-peer link
Right.
but at the same time not cause disruption to the IT traffic, right? Any other IT traffic in Teams or whatever other users are doing in the enterprise. So we see this as brings a lot of value to our enterprise customers.
It's pretty neat because the access point is being like setting the rules. Like, this is how you're going to communicate. I already have this located for you. Please don't make a mess on this side of the woods.
That's right. I mean, it's I would say it's more almost like a give and take. Right?
Yeah. Okay.
Right. No, the reason is because the access point, the infrastructure, right? They also have they want to make sure that the user also is satisfied with his peer-to-peer traffic, right? So I'm sharing the screen in the IT environment. Well, IT wants to make sure that I can work productively when I'm sharing my screen. So there is one side, which is the IT that wants to make sure that me as an employee, I'm able to do everything that I have to do effectively using wireless. But at the same time, IT wants to make sure that when I'm doing that, I don't cause interference with the IT. Right. So it's more like give and takes. Look, I'm going to help you, but at the same time, it's helping me. So it's a win-win situation for both.
Yeah, no, that's I like it. That's pretty interesting.
Yeah.
There are also two other, well, not others, but so we have Wi-Fi 7 and then we have Bluetooth. But in Bluetooth, you have Bluetooth 6 and Bluetooth LE. Tell me a little bit more, well, both, but let's start with LE.
Look, I mean, Bluetooth LE, which stands for low energy, it's really an impressive set of capabilities that we are bringing. So in Panther Lake, we are launching Bluetooth LE. It's much lower power compared to Bluetooth Classic. So we call it usually Bluetooth that people usually use. We call it Bluetooth Classic. Mm-hmm. LE, it's much lower power, right? So just right there, I mean, it makes sure that in mobile platforms like ours that are battery operated, that it lends itself very well to that platform, right? So you don't have to scan so many channels. The physical layer it's a lower power. And one of the cool features that we are launching with Bluetooth LE is Auracast, which is based on Bluetooth LE. Mm-hmm. And so, I don't know if you noticed, but every time that if you're using a laptop with your wireless headset, you can only connect one headset to the laptop.
Yep.
Right. And if you wanna watch a movie, if you're on a plane, if you wanna share that with somebody next to you, you cannot.
Oh, so you're saying I don't have to give my partner the other?
Not anymore.
Yes.
Not anymore. Right. What we're launching now with Panther Lake and Auracast, which is based on Bluetooth LE, you can now share your personal audios with multiple headsets now.
All right, sold. All right.
Right.
Where'd I get this?
And so it's really a cool feature. We can now the PC is going to be able to handle multiple headsets now, right? So whenever you control volume, everything, you're going to be able to see multiple headsets connected. And so we are really excited about this feature. And the other one that we are making the laptop so much more robust now. Mm-hmm. We were just talking about a few minutes ago how in Wi-Fi we can use two antennas.
Right.
If you look at across the board, all the laptops today, they usually dedicate one of those antennas also to be used for Bluetooth. Right? Or they have one which is dedicated for Bluetooth in the platform. What we introduced now is something called dual Bluetooth, mm-hmm. which essentially the ability to also use the second antenna for Bluetooth as well. Right, just like we are doing for Wi-Fi, use two antennas. And so the reason we are doing that is a few, right? First, it increases the reliability of a Bluetooth connection so much more. Mm-hmm. So if you have one side of your laptop that is in a shadow, for example, a shadowy situation, you can use the other antenna now. Right? Oh, nice. It gives you better diversity. We can implement something that is called maximal ratio combining. It gives almost, just to give you an idea of range, it almost doubled the range that we can achieve, right? It goes from our current product, which is about 28, 30 meters, it goes to about 50-ish, meters in terms of range.
That's a long way.
Right? And that is also, by the way, as much as the gains we have over competition too, right? So the range, the competition today is still using one antenna, we are moving to two, we're going to be able to get almost twice the range that other products can get in the market today. So we are really excited about Auracast, about improve the reliability and the robustness of our Bluetooth connections. We can also support multiple Bluetooth connections at the same time, whether you are doing multiple voice streams or calls. And look, these are just some of the stuff that we are launching.